Awesome. Well, thank you everyone for attending today's talks. I found all of them pretty valuable today. And for my part, I wanted to talk about using Python for maintainable HPC or data science and how we can possibly augment what Python can or cannot do with C++. So I want to briefly cover a few topics, primarily compare and contrast C++ and Python for scientific computing applications. Should you be using Python at all? And what are some of the tools or frameworks that currently exist in Python, or specifically the PyData stack? So it's sort of trading productivity and performance here, and how much performance are you actually training for productivity when you use some of these tools? And three frameworks that I want to talk about today for Python is Numpy, Eigen, and Extensor. So Numpy is primarily a Python-based tool or framework. So if you just want to stick within just Python, it's sort of the first place I think that most people should be starting when they're looking to accelerate their code. And if you're delving beyond Python, if there are parts of your code that cannot be accelerated or benefit from Numpy, then you're comfortable using C++, then you may want to look at tools like Eigen or Extensor, which you would use to dispatch computationally intensive parts of your code. And so with that, I'll get started by asking the question, is Python even appropriate for scientific computing? And if you're going to use it for scientific computing, what are some of the pros and cons? What should you know before you get started doing this? So the pros are, it's fairly easy to prototype algorithms, and it results in fairly compact code compared to other languages. And there are a plethora of mature libraries out there specifically for data science these days. It's almost the gold standard now. And what are some of the cons? The first one is no surprise to anyone who's used Python. Native code is slow. There's just no way around it. It's an interpreted language. The second and third ones are fairly subjective. Some people might disagree with me on this, but coming from someone who's coded in Fortran and C++, to me, parallelization is still considered a second-class citizen there. And the ecosystem for debugging, I would argue, is still fairly poor and nascent compared to the C and C++ ecosystem. On the other hand, C or C++, they're the gold standard for scientific computing applications. I would argue that there's probably only Fortran that's primarily used for most applications, although we have a strong contender in the form of nowadays for doing scalable applications. So it's fairly mature for most scientific computing workloads. You have a well-established ecosystem of libraries, tools, and best practices. And you have a plethora of paradigms, honestly, for doing parallelization. The cons are, this is the whole reason for this talk. I mean, what are some of the disadvantages of using C++? It's primarily very slow to develop. And if you want to prototype new algorithms, it's just not that simple as using Python, Julia, MATLAB, which is why a lot of academics and researchers still use these languages. And it makes it accessible to a lot more users than C++. In particular has a fairly steep learning curve, and it can seem inaccessible to someone who doesn't have a very strong background in computer science. I would say if you learned C++ about 20 years ago, the language now with 17, even the 14 standards look completely different. So it can be quite intimidating to someone starting in this language now. And it results in fairly verbose code, making maintainability and debugging difficult. So even if you're an experienced programmer, it results in some fairly large code bases that can become quite cumbersome over time. So maybe there's a way to mitigate this using Python at a high level and just using computationally intensive or writing your computationally intensive code sections in C++. So in Python, the landscape is primarily been shaped around data science. I would say the scientific toolkit of optimized libraries that most people are familiar with are Numpy, SciPy, and Pandas. So this has sort of been the benchmark or the framework set around which data science has evolved. And these libraries are written in optimized Fortran or C or C++, which kind of helps to mitigate some of Python's speed problems. However, we still have limitations that exist for scalable computing. A lot of frameworks do exist right now to avoid some of these problems or minimize some of these problems. For example, PySpark is used predominantly for distributed computing. The paradigm is a little different from something like MPI, but these are still options. So Dask has sort of formed this niche for outer core computing. So it sits in between something like Pandas and PySpark. GPU computing, that is something that has traditionally lagged for in Python. The Rapids toolkit is fast being developed by NVIDIA, and I would say it's a fairly useful and complete tool set for GPU-based computing. So they have several for graph-based algorithms, and there's a scikit-learn port to GPUs and so on. And deep learning, I think by now almost everyone knows these tools. You know, Python is the language for deep learning. You have several frameworks such as TensorFlow, PyTorch, MXNet, and so on. For the PyData stack, which primarily consists of, as I mentioned, Numpy, SciPy, and Pandas, can provide pretty competitive performance while substantially reducing your development time. So these are libraries, as I mentioned, written in C and C++ or Fortran for fast computation. So I provided this link here that actually goes into a lot more detail comparison of these productivity languages versus performance languages, as they're called. So they have some good numbers that detail for you how much performance you're leaving on the table when you're using this productivity language, or how much faster you can develop and prototype an algorithm. These languages can be relatively harder to scale though. So a rule of thumb would be to use these high-level languages to direct your control flow while performing the scalable computations in the performance languages. So I'll start off with Numba, which should be everyone's, your first step if you're looking to accelerate your code. If your sections that are slow and you're using regular Python and things like NumPy don't work, then your first step should always be a decorator-based accelerator framework such as Numba, which is a just-in-time compiler that allows you to accelerate your Python functions or routines using this just-in-time decorator or those functions. So these functions will then get compiled to machine code. Ideally, this tool works best with NumPy functions. So they are optimized or they're written to optimize many of these NumPy functions effectively. It does have the ability to break free from the GIL or the global interpreter log that sort of cripples any sort of parallelization within Python. And you can do that by introducing the parallel equals true flag option to this just-in-time decorator. You have the option to use threading through the Intel thread building blocks or OpenMP. You just have to set the set num threads method here and pass the number of threads you want to use at the beginning of your program. So one easy way that a Numba allows you to parallelize or accelerate your code is loop optimization. So instead of using a regular range, you can use a p-range within Python to parallelize your loops. So it kind of goes without saying, anytime you have these pragma-based optimizations using these frameworks, you have to avoid race conditions, make sure you can actually update these loops in a parallel fashion. So make sure you have no race conditions in your loops. Another way you can accelerate your code is through this fastmath equals true option to the decorator. So that uses the Intel SVML or short vector math library. So these are optimized functions for transcendental math operations. So these are shorter precision operations that are not IEEE compliant. So if that's not an issue for your program or your application, you should definitely take advantage of it. And I would argue that most of these are fairly easy to set up compared to a lot of the C++ frameworks, because most of the times if you're using a package manager such as pip or conda, all you need to do is just conda install NumPy, and then you can even install the Intel short vector math library into that conda environment. And it's fairly simple to use. Now, a lot of times I've noticed that you almost get a 2x speed up when you switch to the fastmath library. So Numba relies on compiling your function code. So you have to make sure that everything that's in your function code can actually be read by the Numba compiler and compiled into efficient C++ code. And for that reason, Numba offers two modes for your compiled function or code. So you have no Python mode and object mode. So in no Python mode, there is no Python interpreter involved at all. So this results in fairly optimized and fast code. So everything gets compiled to C code. So you don't have to call the Python interpreter at any point in your execution. On the other hand, object mode is when it's unable to actually compile everything into C++ code or into machine code. And it only primarily helps with loop lifting or running the inner section of a loop in no Python mode. So suppose you have your routine that has sections that cannot be compiled, or it cannot do things like type inference, and it fails to go into no Python mode. In that case, if there's maybe a section within that's a loop, it can just optimize just that loop while leaving everything else untouched. So most of the times, object mode is no faster than just using regular Python. So if Numba is unable to use no Python mode, then I'll usually just fall back to this object mode unless you specify no Python mode equals true, in which case the compilation would just fail. So if you have Python features in your code that are not supported by Numba, they have a pretty extensive list of features that they say are either partially supported or not supported. So you want to double check that before you actually start retrofitting your code. So as I mentioned, Numba relies on type inference to figure out what type each variable is. And if it can't do that, especially with compound data structures, it can fall back to this object mode. And then you either have to use the object mode or you have to rewrite your code. So two operations or decorators that I want to mention here is vectorize and GU vectorize. So this relies on something called a universal function in NumPy or ufunc. So what happens is it does eager compilation of your function using this decorator that we're passing to this function with signatures. So we're passing as arguments or parameters a signature here. So in this function, you're taking X and Y, and we're saying return X and Y as an output. So this just corresponds to the output. The float 64 is indicating to me that the return value is a float 64. And within that, I am indicating the arguments that are being passed to this function X and Y, which is a float 64. And I'm saying I don't want anything that's not, I want no Python in my compiled code. So that's set to true, and we're setting the target. In this case, it's just CPU. So the nice thing about ufuncs is that you get features such as reduce, accumulate, and broadcast you don't normally have with regular functions. So what it does, it operates on vectors by allowing you to write a function that just operates on scalar. So in this case, it's just performing an addition on two scalars. However, you can also pass a vector array to it, and it would parallelize or vectorize that, and you can use it to just perform those operations by just writing one function here. And I also want to add that this supports a single-threaded or multi-threaded CPUs and GPUs using this target method here. So instead of CPUs, you can pass GPUs if you have a Numba-compatible GPU. So the other decorator is the GU vectorizer, or the general universal function vectorizer. So it's fairly similar to the vectorize decorator we just saw, except it operates on multiple elements at a time. So think of a window function, and if you want to operate on an entire set instead of just one element, if you're adding two, if you're just doing just matrix or a scalar addition on two scalars, instead of that, you can operate on a set of scalars or a vector and a scalar at the same time. However, the syntax now is a little different. Instead of returning the result, and now the result gets passed back through an argument parameter. So here, now we're specifying the list of arguments symbolically like so. So this in 64 or 64-bit integer corresponds to the first argument, and we're saying it's a vector. And the second one is a scalar 64-bit integer. And the third result here is the 64-bit integer vector. And we know it's an output because of the symbolic notation here that says that the first one is a vector of size n, the second argument is a scalar, and the output is a vector of size n. So this corresponds to the three arguments that are shown here. So the problem that I had to solve here is one of multidimensional scaling, where you're trying to do dimensionality reduction. Computationally, it's an optimization problem. And I have the stress function here that I'm optimizing for. And what I want to solve for are the weights here. So it's basically have an inner product of the weighted high dimensional matrix, and you are subtracting from that the lower dimensional matrix here. So you're doing this optimization problem or all the rows of these matrices. And then you want in the backward multidimensional scaling process, I am optimizing for the weights. And in the forward multidimensional process, I am optimizing for the z's. So we'll look at how I sort of optimized, or I used Numpy to accelerate some sections of this code. So because this was a gradient-based optimization process, there's an objective function, and then there's a gradient calculation. So I have some code here that I am using to call this derivative function or the gradient calculation function. So it's kind of similar to the small code snippet that I showed earlier, except for with a more realistic example. So if you look at this decorator here, the first set of arguments or parameters corresponds to the parameters that I'm passing here. So these are all symbolic notation saying I have an unsigned integer, I have a float vector, and so on. And the second set of arguments corresponds to the size. So these are all scalars here. These are arrays corresponding to dimension n row times n row, and so on. And here I'm setting no Python equals true and target equals CPU. So the one thing to keep in mind with using something like Numpy is that you really want a code flow that's similar to this. You want to have lots of stacked calls in Python. So if you just have a single matrix multiplication in Numpy, it's really not going to accelerate it because Numpy is already pretty optimized C code or Fortran code, and it uses plus under the hood. So it'll be pretty fast already. But you have several of these stack calls that are doing operations one on top of the other, then Numpy can really go ahead and perform vectorization and alignment and optimize these sequence of operations pretty well. So just a quick comparison in numbers for a data set of size 48 by 72. I have results that compare pure Python with the Numpy object mode and Numpy no Python mode. So the pure Python code actually took about 0.68 seconds. The Numpy object mode really didn't give me any speed up at all. It was basically the same as regular Python. However, the Numpy no Python mode was 0.08. I believe it was around 80x speed up just by using the GU vectorize decorator. So moving on to the other two frameworks, that is Extensor and Eigen. So if Numpy just doesn't cut it for your application, then you may want to look at profiling your code and then dispatching some of these computation intensive sections to either Extensor or Eigen. So I will say Eigen is definitely the more popular framework here. It is used widely either as a standalone framework for scientific computing, or it's wrapped into a lot of popular packages such as TensorFlow. It has a wide variety of algorithms for doing linear algebra applications and functionality similar to Numpy. Extensor is kind of similar to Eigen. The philosophy is that the syntax is supposed to have this one-to-one correspondence to Numpy. The one advantage that Extensor does have is that it provides Python bindings to make it easy for you to transfer data structures between Python and C++. So you can just pass your Numpy data structures to your C++ code and perform computation within Extensor and pass it back. So it's fairly seamless, unlike with Eigen, where I have to use a framework such as CFFI to transfer data to it and bring it back. The one downside, however, is that this is a fairly new framework. It's not quite as widely adopted yet. So it is, as I mentioned, Eigen is one of the most popular C++ libraries for numerical computing. It has a fairly expressive and intuitive API, I would say probably the closest to Numpy in terms of ease of use. It uses broadcasting and lazy evaluation to accelerate your code. And it is used by a lot of frameworks out there under the hood. Frameworks such as TensorFlow and Stan are built on Eigen. Therefore, I would say it's fairly reliable. So you can depend on it to not break on you most of the time. Eigen is fairly easy to compile and use compared to a lot of C++ frameworks. It's a header-only library. So all you need to do is just provide the path to your Eigen, and you can just compile and link to your code. And it alleviates a lot of the compilation headaches that people come across when you're using these C++ frameworks. So does it come close to the Python productivity that we see in tools such as Numpy? My personal opinion is it gets as close to Numpy as possible while providing you all the speed benefits of the language C++. It provides fast vector and matrix operations using static or dynamic containers. For static containers or compile time specified containers, you have up to 4 dimensions. So you can use either vectors or matrices of dimension up to 4, and you have associated operations or functions you can call on those. So in terms of operations and matrices and vectors, you have quite an extensive list similar to what you would find in Numpy. You can call the sum, the product, trace, and so on. You can also perform block operations. For example, I can say I want to extract a subset of the matrix starting at ij of size AB as shown here. And you can do row operations and column operations using the row or column method as well. You also have these coefficient operations that you can call on each one of these individual elements in these vectors and matrices. Apart from that, it has a fairly robust set of algorithms for performing linear algebra. So if you're looking to perform things such as LU decomposition, QR, eigenvalue SVD decompositions, they have a fairly comprehensive list of popular algorithms along with a benchmark list that I've given here for their performance scalability characteristics. So it works on dense and sparse matrices. So you're not just limited to using dense matrices. If you have a really large matrix, you can use some of these direct and iterative solvers for these sparse matrices. The one thing to keep in mind here is that some of them do require that you use external libraries such as GPL. They just provide wrappers in here for you to interface, but it might require that you actually install them before you could use them. So I'll just walk through a small snippet of the code that I used to do basically the same thing, which is the multidimensional scaling. And I just wanted to give you a sense of what it looks like in Eigen compared to Python. So here, I didn't actually find a way to easily load a CSV, so I had to write my own custom loader for that. But other than that, I would say the syntax is fairly similar to what you would find in Numpy. You have, for example, extraction of your shape and size by calling the column method, the row method here. So you notice in this operation here, I have this method called noAlias. This is because Eigen creates temporary matrices when you're doing operations in order to ensure correctness, especially when you have something like matrix multiplication on the same matrix. So you can specify explicitly saying, explicitly hinting to Eigen that we do not want to create a temporary matrix, and therefore, providing some optimization there. So another example here is of this loop assignment. So I'm computing this element-wise multiplication here. So anytime you see this array method attached to a data structure here, what it's doing is I'm converting from a matrix to an array data structure. So normally without that, this would just be a vector-vector multiplication. But when you're converting it to an array, you're doing this coefficient-wise multiplication here. So in this loop, I am performing this coefficient-wise multiplication, and I'm assigning the result to this row in this term 1. However, it's probably better if you can sort of reformat that problem and think about it a little bit and say, instead of doing it row by row and performing that within a loop, I turn that vector multiplication into this matrix multiplication. So I'm taking the entire matrix X here, and I'm expanding this weight vector here into a matrix by using this replicate method. And I'm just performing that in one command here instead of looping through it. So things like these would definitely go a long way towards helping Eigen optimize your code. You can also use threading. So you're not just constrained to just vectorization. You can take advantage of threading using OpenMP or TBB. Here, I'm using the OpenMP pragma parallel to optimize this loop here. So depending on the capability or the framework you've installed, you can use the vectorization that Eigen provides along with this threading capability provided through OpenMP as well. So Another way to get some speed up to minimize some of the data transfer costs is by memory mapping your data structures. So sometimes when you're passing data from Python to C++, or you're moving it from other data structures, you might have to just copy it explicitly, but Eigen makes it easy for you to interface with raw C++ buffers by memory mapping your data structure. So you can operate on a regular C++ array. However, you can just cast it to an Eigen data structure. So you can now proceed to compute or perform Eigen operations on them without actually having to perform the copy here. So they provide this method called map. The syntax is probably not the most elegant there, but you still have the capability to say, I just want to move that data buffer, that is, it's a C++ array, and now just Eigen sees it as an Eigen data structure, so I can call these algorithms on that data structure. Quick comparison of the subroutines in C++ and Python for various data sets. So I noticed anywhere from a 23x to 32x speed up here. Although I did notice a interesting declining trend as I am changing the data set. I need to look at that a little bit more to see why that is happening now. And the last framework I wanted to talk about is Extensor. It's a fairly new framework. Unfortunately, I don't have a lot of guidelines on how to optimize it, but they're trying to evolve the documentation on their website, so hopefully more information will become available. It is a fairly well-designed library. It is intended to be similar to Numpy. So they have, as I mentioned, a good correspondence with Numpy. There's actually a page here. If you go to this link here, it'll give you the equivalent extensor call for every Numpy call. And it has the same Numpy style broadcasting and lazy evaluation that you would find in Eigen as well. As I mentioned, the one advantage for that is you had this Python bindings from the Python 11 library. And you can pass these Numpy data structures fairly seamlessly using this Python buffer protocol. So if you are using Anaconda or a pip environment, it's fairly easy to install Extensor. You can just install that into your Anaconda environment. And in order to compile your C++ code, all you have to do is just provide the path to that Extensor environment. So now you have just one place where your Python code and your C++ code all exist. And if you want to call that your shared object C++ code from Extensor Python, all you'd have to do is just compile your C++ code into your shared object library. So I've provided the syntax here, and this flag is what you need in order to be able to call that from your Python code. So how do you actually do that? Once you have that compiled into a shared object library, you just import that as shown here. And this is the entry point from the C++ code. So I am saying from Extensor, call this routine and then pass my Numpy data structures to it. So I haven't changed anything in my Python code. All I have to do is just pass my Numpy data structures to that shared object library and that routine. And within that shared object library or the C++ code, the first thing to do is I have to declare an entry point. So that's within this function called the pybind11 module. And I have to call this import NumPy method before I can actually use any of the NumPy data structures. The actual declaration is assigned right here that says this routine within this code, within the C++ code, is where I can expect my computation to start. So looking at what that code looks like, essentially the argument for that, this is the mapping between the NumPy data structures that we pass to it, which are all now mapped as a pi array. And once you have that extensor pi array, you can just pass that along and perform computations in the extensor syntax like you would normally do with any C++ code. So I'll wrap up quickly. So I have this code here just so you can get a sense for how it compares to Eigen. They do say that it's the syntax is supposed to be similar to NumPy. I mean, it's fairly subjective to me. It's nowhere near as elegant as NumPy yet, However, they do a fairly comprehensive mapping with the functionality. So you do get a lot of the functions that are implemented in C++ available in Eigen. In Extensor. So originally I had used this framework just to pass data back and forth, and I did my computation in Eigen. So this is essentially a port of the subroutine that I showed you earlier. It's basically a matter of preference at this point because I didn't see much of a speed difference between Eigen and Extensor. I would argue that Eigen was probably a little faster. And if I had to pick one, I would probably use Eigen. However, I cannot overstate the convenience of being able to pass data structures between Python and C++ seamlessly in Extensor. So when I did actually use Extensor as just a wrapper framework to pass data structures, for this data set at least, less than 4% of the time was spent just transferring the data and initializing the routines. And in conclusion, wrapping up, the things that I want to leave you with is native Python is slow, but we already knew that. Profile your code as much as possible and scale up your code and performance incrementally by adding complexity slowly. So first step is obviously to use optimized packages, but most people already do this. And then your second, the place you should start is in my opinion, at least Numpy. It provides the easiest way to accelerate portions of your code with minimal impact or changes. And if that doesn't work, use a framework such as Eigen or Extensor if you're comfortable with C++, and you can always add multi-threading to it if you need to take advantage of parallelism. And with that, I'll open up for questions if I have any time left.